All right, Chapter 9, Think and Explain. Number 50, comment on whether not the following label in a consumer product should be a cause for concern. Caution! The mass of this product pulls on every other mass in the universe with an attracting force that is proportional to the product of the masses and inversely proportional to the square of the distance between their centers. All right, so this comes down to, I think, philosophically, deals with what is meant by a product. So this textbook, for example, is the product. The textbook itself, or is the product the actual atoms themselves and the subatomic particles within it? So at what point? And so if it's the book itself, then this book was probably printed a couple years ago. It takes time for the signal, the gravitons, to actually be transmitted through space because they travel at the speed of light, and it does take time for light to get there. By now the gravitons have gotten Alpha Centauri, but has it gone to other galaxies yet? No, it hasn't. Not for the book itself. Now, if you consider the product to be the things that go into it, which in business is not really considered the product, those are considered to be the resources. Those things were created long before that. The atoms that are in this and subatomic particles and the energy that was in this was created long before, and then that might have time to reach everything in the universe. So, cause for concern? No. But a cause for someone taking it a little bit too far, or maybe I'm the one who took it too far. Yeah, that's your call. 52. What would be the path of the moon if somehow all gravitational forces on it vanished to zero? Classic Newton's second law. Or sorry, Newton's first law. Well, it could be the second. Object will travel in a constant velocity unless acted on by a net outside force. And so if all the gravitational forces acted on it, that means that there's no forces acting on it unless it crashed into something or somehow it was charged, which it wouldn't be. So, yeah, because the magnetic field from the moon is zero pretty much at this point. So the gravitational force acting on it, it should just travel in a straight line. So it would be orbiting, and then it would just sort of go off. 54. Is the force of gravity stronger on a crumpled piece of paper than an identical piece of paper that has not been crumpled? All right, so the spirit of what he's asking for here is the mass of the paper has not changed, and therefore the gravitational pull should still be the same, assuming that it's the same distance from whatever gravitational body you're talking about. So for instance, gravitational force on the piece of paper from the Earth acting on it is roughly the same piece of paper here, piece of paper crumpled. So this is basically the scenario we're looking at here. Yeah, roughly the same to however many significant figures you want to go out. However, we can get into the subtlety of it, of the gravitational force here and the gravitational force here. If their center masses are the same, notice the distribution of mass here. Some of it's closer, some of it's farther away. And if it were linear, so over R, that's inverse linear, you could get into an argument over the gravitational pull at this point is different than the gravitational pull at this point, well beyond the scope of 110. I think in that case right there, if you actually wanted to get into the real subtleties and you're going out, 20 decimal places, then I think this would have a slightly more gravitational pull on it. Again, not the spirit of what he's going for here. Now, he does an example in the solution of if you drop the pieces of paper, the crumpled paper falls faster. That's not because of the weight of the object, but because of the air resistance. There's an additional force that is more significant. 56. An apple falls because of the gravitational attraction to Earth. How does the gravitational attraction of Earth to the apple compare? Basically, I've made the argument in class that since the gravitational force depends on the two masses, if commutative property holds, in other words, if I flip the two masses, I should get the same answer, and I do. This is also classic Newton's third law. Earth pulls on the apple with the same force that the apple pulls on the Earth. Just that because the apple's mass is so much less, it's much more affected by that force. Number 60. Astronaut lands on a planet that has twice the mass of Earth and twice the diameter. How does the weight differ? So his mass, assume, is the same on both. Mass of the planet doubles, so that would tend to double the amount of force acting on him, but the diameter is twice, also the radius is twice, and therefore the distance from him to the center is doubled, but that gets squared. This is similar to some other problems that we've dealt with earlier in this chapter. So ultimately, he would weigh half what he does on Earth. Why do passengers in high-altitude jet planes feel the sensation of weight while passengers in orbiting space vehicles, such as the space shuttle, do not? Please note that in the space shuttle, they still have the gravitational pull. That is why they are orbiting. And yes, it does say orbiting. If the gravitational pull were not there, it would not orbit. The difference is what we generally feel by weight is how much we are pressed against the surface. So again, scales measure normal force, not officially weight. And so because in the orbiting spacecraft, the seat is falling at the same rate that the person is, you actually don't feel that force pressing between them. But on a jetliner, you are feeling that force because you're being pulled down and the plane isn't falling. If the plane were in free fall, you would feel that. There's a OK Go video in which they're in a plane, and I cannot remember the name of the song, but they basically never leave Earth. I mean, there's an example there. It looks like they're floating around, but they're just in the plane that's in a sort of parabolic arc, and so there's that moment where the plane is falling at the same rate that they are, and it looks like they're floating because they're not pressed against the surface. 64 is the gravitational force acting on a person who falls. Is the gravitational force acting on a person who falls off a cliff on an astronaut inside an orbiting space shuttle, similar to the other one? Yes, there is gravitational force. Falling off the cliff, yeah, otherwise I don't think it'd be called falling. And then orbiting space shuttle, oh, here comes Bohr again. You want to say hey to the camera? Yeah, you can see his nose there. And inside the space shuttle, it would not be orbiting if there were not the gravitational pull. And is that it for Think and Explain? Nope. Next page. Page number 83. The value of g at the Earth's surface is about 10 meters per second squared. Value of g at a distance twice the Earth's radius. We dealt with something similar to this before, that it is, if you double the radius, you are quadrupling the denominator because you square that 2. And so the acceleration due to gravity should be about 2.5 meters per second squared, or 2.45 for those who live a bit more pure on that. And that's it for the Think and Explain.